All right. Example first, a max heapify example. All right. In this example, we need to do that max heapify operation. All right. So here, let's imagine the scenario. At the beginning, we have a max heap. And suddenly we detect at one node, there is a violation. Okay. So here, the violation node is in dark color. So you can see it in gray color. So you can see it here. So now we need to fix it. We need to use our heapify operation to reconstruct a max heap. All right, recover the max heap. All right, so here, compare the values. This one has the max value locally here. So based on our operation, we should do one swap operation between these two nodes. One swap, just one. Okay. So after that, we get that. But after that, there is another violation around this node. Yeah. Then the max value of all these three nodes. So we should do another swap between these two nodes. All right, so after that, then we get a valid max heap. So you can see, so simple. Yeah. So you can see, if you detect one violation anywhere in the original max heap, we can fix it through this kind of local fixing. So that's the local fixing, okay? So local fixing. We do not need to go to other places. So we only want to do fix operation locally. Yeah, so that's our meaning, local fixing. All right. So now we want to estimate the cost of the step. So there is a cost. How much is the cost of this max heapify operation? Okay, one such operation. All right. The heapify cost. Heapify. So here it depends on how long is the path, right? So you go along some path, right? So remember, you go along some path. How long is the path? That corresponds to the cost, okay? So our estimate is bigger of log of n. So why log of n? So the understanding is pretty simple. Yeah. First, we have total n nodes. Remember, our heap has the structure nearly complete. Binary tree, right? Has this structure. With this structure, it is a quite balanced binary tree. Okay, quite balanced. It's a complete, nearly complete. So quite complete, quite balanced binary tree. Okay, with this structure, the height is approximately this much. You know, may not be exact. Okay, so +1. You know, there could be one difference, right? Yeah, not too many. So one level difference. So that's the worst case. So at the worst. So that's why the cost is big O of this function. Yeah. So that's, remember, that's our goal, right? When we have dynamic data, after one new data item is inserted somewhere, you know, somewhere, okay, yeah. Yeah, I mean, so usually, yeah, somewhere, right? Yeah. So then we need to fix it. So when we fix it, the worst case, this much. So remember, that's the goal we want to get. Okay. All right. That's the first example. Our second example, now we need to build a whole heap starting from arbitrary array. So we want to construct a heap. All right. So this is the given array. Yeah. Arbitrary. Yeah. Now, so let's build a heap. Okay. To build a heap, we know we need to use the location. So here, because think about the first element, we leave it blank. Okay. All right. Location 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 locations. So then we arrange these 10 nodes in a nearly complete binary tree like this. So 1 here, 2, 3, like that, 4, 5, like that, 6, 7, 8, 9, 10. In that way. So the straightforward arrangement. Okay. All right. Next, we need to fix. We need to check the max heap property because that may not be true. So we need to do detection. Max heap property detection. Okay. When we detect violation, we need to fix it. All right. So here we do the, so how do you do the detection, right? So here we use the bottom up method. Bottom up method for the detection, okay? All right. When we start, let's start from the bottom, the first non-trivial structure. Yeah, because the first, when we look at this, there is no violation. Yeah. The first subtree with heap relationship, no violation. So we go to the next one. Next one, we look at this subheap, right? Yeah. There is a violation. We detect there is a violation. Okay. So then we fix it. Okay. So we swap these two nodes. Okay. Yeah. So we fix this locally. Okay. All right. So we move up another level up. Next, we try to fix this subheap structure. Maximum value here, so we need to do swap between these two nodes. Okay, yeah. Then after another swap, we get this. All right. But after that, the next subheap, this one, you can see another violation detected. Okay. So to fix it, swap operation between these two, because the 16 has the maximum value. Right? After that, so 1 is here, 16 is there, but another violation here, right? Yeah, another violation. So we need to do another swap between these two nodes. Okay, all right. So after we fix that, we get that. All right. Now, bottom up, we reach the top. Now we need to fix the whole heap with root at this point. Okay. So when we do it, the max value here, so we need to do swap operation here. Okay, then going down. So let's look at after that swap. So 4 is here. 4 is here because there is a possible violation here. So we need to compare with it the values of 2 of its child nodes. So we detect another violation. So we should do swap between these two. After that 4 here, another violation. So another swap after that. Okay. All right. So after those operations, then we get the whole heap. So after that, bottom up, after we process all the possible locations, then now we have a max heap. All right. So that's the whole procedure constructing a heap from any given array. Yeah. And here, the next we need to consider the cost. Is this construction procedure very expensive? How much is the cost? So we want to have that estimate, the cost estimate. So that is very important. Yeah. But we will do it in our part B. The next lecture, yeah, part B. So we will do it. Yeah. Lecture 8B. Yeah. We will do that analysis. After that, then the heap sort. Because finally, we need to do the heap sort. Okay. After that, another problem we need to solve, the binary exponentiation. Another problem we need to solve. Yeah. So that's the next lecture. All right, so we complete this lecture 8 part A here. All right.